Okay, conservation of momentum. So what we're talking about here are collisions and explosions. So two objects colliding, that'd be like this right here. Here's a collision. Two objects pushing apart from each other, that would be like a cannonball being fired from a cannon. We would call that an explosion, two things pushing apart. Now, in order for this to be true, the only force acting on the objects in the collision or the explosion is the force of the collision itself, right? So we're saying for all these problems, no friction, no force of an engine, nobody has their foot on the brakes, you know, that'd just be another example of friction. So the only force present in these problems will be the force of the collision, and if that is true, then the initial momentum before the collision or the explosion will equal the final momentum after the collision or the explosion. Now, yesterday we talked about the equation for momentum. Momentum is the symbol P. It's mass times velocity. Now, when kids first look at this equation, they're like, what? All these M's, all these V's. It's really pretty simple. What would M1 V1 initial be? That's the initial momentum of object 1. What would M2 V2 initial be? The initial momentum of object 2. So you take them, you add them together, it's your total starting momentum before the collision or the explosion. And then the right side of the equation, you have M1 V1 final, the final momentum of object 1, and then M2 V2 final, the final momentum of object 2. Initial momentum equals final momentum. Okay. Now what I'd like to do is go through a quick derivation of why this is true, and then we'll do an example. So this pertains to yesterday's lecture. So what we have here is, we'll call this guy number 1, this will be guy number 2, and they're exerting a force on each other. It's like an explosion, and they're on a frictionless surface. No friction. Okay, we got to remove friction. We're going to say to the right is plus, to the left is minus. So guy number 1 exerts a force on guy number 2. So we're going to call that F12. So see right here, F12. The way you interpret that, it's the force from guy 1 on guy 2. And then what is guy number 2 doing to guy number 1? Exerting a force this way. So we'll call that F21, meaning the force from guy number 2 on to guy number 1. So is everybody with me? Now, dudes, what do we know about these two forces? They are equal and opposite. Okay, so these guys, they're going to push apart from each other. They're equal and opposite. Now, yesterday we talked about force time graphs. Okay, hold on, let me grab this. Okay, we talked about force time graphs. I'm going to make this a little bigger. Why is it not? Oh, well, it doesn't want me to go bigger. Okay, on a force time graph, the area under the graph is the change in momentum. So yesterday I gave you this equation. Change in momentum is equal to force multiplied by time. And if you take the area under a force time graph, really what you're doing, you're going base times height. So what's the base measured in? Base is time, the height is force, and you would need calculus here because it's curvy, but pretty much what you're doing is you're multiplying base times height to find the area, which is force multiplied by time, which is the change in momentum. Do you guys remember this from yesterday? Area under a force time graph is the change in momentum. So this would be the change in momentum for guy number 1, and then this right here would be the change in momentum for guy number 2. Okay? What do we notice about these two areas? They are equal to each other. It's the same area. And you know what? When we get our force sensors, I'm going to have you guys do collision experiments where you're going to get data that gives this exact graph. And keep in mind, this time interval here, the time interval we're talking about, like the time right here, would be like 0.1 seconds. It's a very small time interval. Oh, and another thing I want to mention, notice how this graph goes up and then down like that. And that's pretty much what happens when two objects interact with each other. Like as these two guys start to push on each other, the force gets bigger, bigger, bigger. It reaches a maximum, and then as they come apart, the force drops back to zero. Does that make sense? So what we're saying here is this. The change in momentum for guy 1 is equal and opposite to the change in momentum for guy number 2. Right? That's what we see from this graph here. Now, what's change? Change is final minus initial. So this is momentum 1 final minus momentum 1 initial. And then this is going to be negative. We have a negative right there. Negative momentum 2 final minus momentum 2 initial. Distribute this negative. Momentum 1 final minus momentum 1 initial. Distribute the negative. We're going to get momentum 2 initial minus momentum 2 final. Rearrange one more time and look what you get. Momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. What is this equation right here? It is this. It's the conservation of momentum equation. So when two objects collide or explode apart, the force on each object is the same, and the time of contact, the time that the force acts for, is the same. So when you calculate these areas under these graphs, the area is the change of momentum. The change of momentum is equal. They're equal and opposite to each other. And then you can do this. Okay, so let's get to an example here. All right, so we have a situation where a 1,200 kilogram car, so let's say the car is M1, 1,200 kilograms, rear ends this truck, which we're going to say is M2, that's 9,000 kilograms. So this velocity here is V1 initial, this would be V2 initial. So here we have before, and we have after. So this is V1 final, and then this right here is V2 final. So what they want you to find in this problem is the velocity of the truck after the collision, and then the second thing is the loss of kinetic energy in the collision, which I'll talk about in a minute. So why don't you guys take like 10 minutes. The answer to number 1, if you do this correctly, you'll get 20.93 meters per second. And then the answer to number 2 comes out as 8,680 joules of kinetic energy lost. All right, so we'll give you 10 minutes. So here's how you do the problem. Now, hey, I'm not going to have you guys watch me do the algebra because that'd be kind of boring. But look, if you look at this conservation of momentum equation, the only thing missing is V2 final. You have everything else. So you do the algebra and you get 20.93 as the final velocity of the truck after the collision. Now, the second question is a little more challenging. It's asking for, close this. Okay, it's asking for the kinetic energy lost in the collision. Now look, in 90% of the collisions that you're going to see, in 90%, kinetic energy is going to be lost. You're going to lose energy. And where does the energy go? Well, if you look here in the diagram, one reason I chose this picture, what do you notice about the front end of the car? It's jacked up. It got all smashed in. What do you notice about the back end of the truck? It's all smashed in. Does it take energy to like crumple the front of your car? Yeah, and that's where the energy goes. So even though momentum is conserved, you know, if the only force present is the force of the collision, momentum will be conserved, but you're going to lose energy in about 90% of the collisions that you're going to see. Now there's a buzzword. When you see this word, if they say the word elastic, what they're telling you is that energy is not lost. If you took AP Chemistry, who's taken AP Chem? Does that word sound familiar? If a collision, gas molecules. When gas molecules collide with each other, That's referred to as an elastic collision. You know, gas molecules go like this. They go do, 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 do. When they hit, do they slow down at all? No, they keep their kinetic energy. So if you come across a problem where they say that the collision is elastic, then they're telling you that the kinetic energy is conserved. But if they don't mention the word elastic, then that means that kinetic energy is lost. And where does that energy go? Why are we losing energy in the collision? Because it takes energy to deform an object. All right, so here in this problem, we are going to lose kinetic energy. So here's how you calculate it. What you got to do, if you're going to find out how much you lost of something, you got to know two things. How much did you start with, and how much did you end with? So before the collision, we have two kinetic energies. We have kinetic 1 initial, and we have kinetic 2 initial. The car has kinetic energy, and the truck has kinetic energy. So the kinetic energy of the car, you do 1/2 mv squared, you get 375,000 joules. For the truck, you get 1,800,000 joules. Add those two together, and you get 2,175,000 joules. That is the total kinetic energy before the collision. Now, do the same thing for after the collision. After the collision, so we're going to go kinetic 1 final. So the car has 194,400 joules. The truck, kinetic 2 final, is 1,971,920. You add those together, and you get 2,166,320 joules. So that's the final. So how do we figure out how much kinetic energy was lost? This was the kinetic energy before. This is the kinetic energy after. So how do we figure out how much was lost? Subtract them, and we find out that we lost 8,680 joules. That was the energy lost in the collision.
Wait, for the kinetic energy 2, I got 1971292.
Oh, you know why? Don't use a rounded velocity for this. You don't want it. I would use the whole value, because it was 20.93 blah boom boom boom. Use the whole thing. If you use the unrounded, then you should get that.